Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering, and we'll extend our discussion on thermal properties of materials. So far we have discussed various thermal properties, starting with the very foundation one, that is heat and temperature, then specific heat, heat capacity and water equivalent. Then we discussed about the change of state of a material and how a material goes through the three different states of existence, that is from solid to liquid to vapor. In that video, I just touched upon the concept of latent heat. Okay, so if you remember, let me just recapitulate it a bit. So basically we have a substance. It can exist in three possible states: solid, liquid and vapor. We took the example of the simplest explanation, the simplest experiment, that is ice, water and water vapor, the change of these three states. And we found out that these change of states, that is the transition of a substance from one state to another, it can be categorized into different categories. Solid to liquid, that is heating, that is called as melting. Liquid to vapor, that is vaporization. The reverse, liquid to solid through cooling, that is freezing. And vapor to liquid, that is condensation. Now the basic law says of heat and temperature, it says that if there is a substance, okay, if there is any object and you supply heat to it, its temperature should rise. If you take heat away from it, okay, if you take away heat away from it, its temperature will drop. Okay, now we also know the basic principle that if two objects are at different temperatures, one is at a higher temperature, one is at a lower temperature, heat flows from higher to lower till both the temperatures are equal, which is called as the thermal equilibrium temperature. Now this is quantified through the concept of heat capacity, which is the amount of heat required to raise the temperature of a substance of any mass through 1 degree Celsius. Now if we specify it further by categorizing or specifying a unit mass, that is 1 gram or 1 kg, then the amount of heat required to raise the temperature of a unit mass of substance through 1 degree, that is called as specific heat. So in either case, you will see that whenever there is application of heat, there is always an increase in temperature. This is the basic law. The reason why I am again repeating all this is so that you don't get confused. You know where I am starting from, the baseline, the reference. So this is the thing that we have studied so far. Now what happens in this simple experiment that we conducted, where we took some ice cubes, simple ice cubes, which were at temperature a little below 0 degrees Celsius, that is negative, and we started heating them on a burner. And what we did is we measured the temperature continuously, and we started a plot of the temperature versus time graph, where temperature was measured in Celsius in the y-axis, time in minutes in the x-axis. Now what we found out is that at this temperature, starting temperature, which I deliberately took a little bit below 0 degrees Celsius, where it is the starting point. As we started heating, the ice was still in the solid phase. Okay, it is in the solid phase, and the temperature started to increase. Okay, it started increasing till it reached 0 degrees Celsius. Now I always tell that this is a special temperature. 0 degrees Celsius is a very interesting special temperature when it comes to ice, water vapor, transition. So this 0 degrees Celsius, at this temperature, when it reached, the ice is still in the solid phase here. Now what happened? The temperature remained constant. Even if we kept supplying heat, even if more and more heat is supplied, the temperature remained constant without any increase till it reached this point. Again, this is at 0 degrees Celsius. But here it is water, liquid water. But here it is solid ice. So both solid and liquid, ice and water, coexist in thermal equilibrium at 0 degrees Celsius, and this is called as the melting point, 0 degrees Celsius, and it is chosen as one of the lower reference temperatures in the design of thermometers. Okay, this is the concept of melting point. Now after that, again, as we keep on heating the beaker where we have taken the ice, we took the ice cubes initially. When we kept on heating, more and more heat is supplied, the temperature again increased. Okay, it again started to increase until it reached point D. Now this point again is another special temperature in reference to ice water vapor transition. This is 100 degrees Celsius. Now at this stage, at D, it is still water in liquid state. And as we cross this point D and we kept on supplying heat, the temperature again remained constant. It again remained constant till we reach this point where the water becomes in vapor state entirely. The entire liquid got converted into vapor, and until then the temperature didn't increase. Here, until the entire solid ice got converted into liquid water, the temperature did not budge a bit. It remained still at 0 degrees Celsius. Here it remained still at 100 degrees Celsius till the entire liquid got converted into vapor at E. So here 100 degrees Celsius is the temperature at which liquid water and water vapor, they coexist in thermal equilibrium at the same temperature. This is called as the boiling point. This 0 degrees Celsius is the melting point. This is the boiling point, 100 degrees Celsius, and it is taken as another higher reference temperature for the design of thermometers. Now again, beyond E, when we kept on supplying heat, the temperature again started to increase. So these two are two unique special temperatures: boiling point, melting point. Okay, boiling point and melting point, which involves the transition of ice to water, then from water to vapor. So melting point is this, the temperature at which the solid and the liquid states of a substance, it coexist in thermal equilibrium with each other, and it is defined by the standard atmospheric pressure. And the boiling point is where the liquid and the vapor states, they coexist in thermal equilibrium with each other. Okay, so here all of this, BC is the melting of ice into water at constant temperature. D is the vaporization of water into vapor at constant temperature. And here it is totally in ice state from A to B. Then from C to D it is liquid water, and from E to F it is entirely water vapor. But BC involves ice water coexistence. BC is ice water coexistence. dE is water, that is liquid, and vapor, water vapor coexistence. Both of them coexist in thermal equilibrium. Now, the main topic here, latent heat. So what happened? The reason why I did all this to make it a point, to make you understand the significance of latent heat. Now, why did the temperature did not increase from B to C and D to E? Let me use a different curve, okay, a fresh one. Okay, why the temperature it did not increase from B to C and D to E? Why? The basic law says that if we supply heat, there will be a rise in temperature. That is the basic law. It is defined by heat capacity, it is defined by specific heat, it is defined by molar specific heat, and it is defined by water equivalent, whatever it is. But why did not it increase from B to C, that is from ice to water coexistence and from water to water vapor coexistence? Why it did not increase at 0 degrees Celsius and it did not increase at 100 degrees Celsius? The reason is that this extra heat which is absorbed here and it did not manifest itself in a rise in temperature, that becomes hidden, or absorbed, and that is why it is called as latent heat. And this extra heat is utilized in converting, this extra heat, it is utilized in converting the total of ice, the total ice entirely into water. Complete conversion. Complete conversion. This latent heat. First, in this stage, that is BC, to completely convert ice into water, and then at DE to completely convert water to water vapor. Even though it shows there is some water, but here the entirety is converted into water vapor, not even a single drop left. This extra heat is utilized to do that. Now, in all of the other situations, that is A, B, C, D, E, F, there is no two-phase coexistence. Here it is only, in CD there is only water, in AB there is only ice, in EF there is only water vapor, but here there is water vapor coexistence. Here there is ice and water coexistence. This is the situation. So to convert entirety of ice to water, you need latent heat. To convert entirety of water to water vapor, you need latent heat. So this latent heat to convert entirety of ice to water, that is called as latent heat of fusion, and this latent heat which is required to convert the entire water, liquid water to water vapor, that is called as latent heat of vaporization. This is the concept of latent heat. So when a solid changes into liquid or a liquid changes into gas, it absorbs heat. But this absorbed heat is not exhibited through an increase in temperature, and it is used to change the state entirely. And that's why it is called as latent or hidden heat. And the mathematical expression here is that, so the amount of heat required to change the state of a unit mass of substance. So here unit mass means either it can be 1 gram or 1 kg at constant temperature. So in case of ice, water change, it is 0 degree Celsius, and in case of water to water vapor change, it is 100 degrees Celsius. Melting point, boiling point. Only for water, ice, water vapor. For others, it is different. Now this is called as the latent heat of the substance. So the amount of heat required to change the state of a unit mass of substance entirely. Here I will add another thing. Entirely. Not even a shred left. So at constant temperature and pressure, that is called as latent heat. So here, if a substance of mass m undergoes a change of state from one to another, whether it is solid to liquid or liquid to vapor, the amount of heat required for the process is Q is equal to ml, where m is the mass of the substance, L is the latent heat. And this is hidden heat, which is not exhibited through rise in temperature. So there are two heats: latent heat of fusion, which is the amount of heat required to change the state of a unit mass of substance from solid to liquid. That is, in case of the experiment here, ice to water at its melting point. For ice water, the melting point is 0 degrees Celsius. Similarly, the amount of heat required to change the state of a unit mass of substance from liquid to vapor, that is water to water vapor, at its boiling point, that is 100 degrees Celsius. For ice, water vapor, that experiment, that is called as latent heat of vaporization. This is called as latent heat of fusion. Now, if you want to go into the in-depth analysis, you can search the thermodynamics playlist where I have explained in detail. So here I will just say that without going much into the deeper analysis, because it is not that much required in material science. So the latent heat of fusion of ice for 1 kg of ice, which is, let's say, initially taken at minus 20 degrees Celsius, the latent heat of fusion is this much: 80 calorie per kilogram, which is 3.33 into 10 to the power 5 joule per kg. And the latent heat of vaporization for water to water vapor, that conversion is 540 kilograms per kg, which is 22.6 into 10 to the power 5 joule per kg. So here we conducted, an experiment with minus 1 kg of ice, which is initially at minus 20 degrees Celsius, and it did all the same things which I discussed. That is, from A to B there was only ice, there was as heat supplied there was increase in temperature, then there was constant temperature at 0, and again at 100 there was constant temperature, and the same thing. But this is the plot here, the detailed plot, where there is heat in kilocalories in the x-axis. Here if you see heat in kilocalories in x-axis, here in the y-axis we have temperature, whereas in the other plot it was time versus temperature. Okay, it was time in minutes versus temperature. Here it is heat supplied in the x-axis and temperature in the y-axis. As you see, at BC, even though heat is supplied, okay, slightly below 50 up to 100, the temperature is still 0 degrees Celsius. And again DE, here, even though there is increase in heat, temperature is constant. So this is the latent heat of fusion, 80 kilocalorie per kilogram, or this much value, and this is the latent heat of vaporization, which means this much amount of heat will be absorbed to convert entirety of water to water vapor, and this much heat will be absorbed to convert entirety of ice to water at constant temperature or thermal equilibrium. And this amount of heat will go hidden, absorbed, without causing any increase in temperature. Okay, so this is the thing here. Let me specify it. So let me do this in red so that, yes. Okay, we need 80 kilocalorie per gram or 3.33 into 10 to the power 5 joule per kg of heat to melt 1 kg of ice into water at 0 degrees Celsius, and we need 540 kilocalorie per gram or 22.6 into 10 to the power 5 joule per kg of heat to boil 1 kg of water to water vapor at 0 degrees Celsius. This is the latent heat of fusion. Latent heat of fusion, and this is the latent heat of vaporization. Okay, this is the significance of latent heat. So for the change of state of a substance, or a material, we need both specific heat concept plus the latent heat concept. We need both. Okay, specific heat is basically heat supplied, increase in temperature. Okay, heat supplied, increase in temperature. Latent heat concept, heat supplied, temperature is constant, but change of state from one state to another entirely. Okay, this is the basic concept here. Now, another interesting thing here is that this is only for ice, water, water vapor, that transition. For other materials, these heat values will be different, the temperature values will be different, the time values will be different. But the overall nature, the overall structure of the plot will be the same. Here, the slopes may be different, the time duration for which the temperature is constant, that may be different, or the amount of heat required to change the state at constant temperature, that may be different. But the overall foundational principle will stay the same. That is, when there is any change of state, it will be happening through latent heat at constant temperature, and whenever we are supplying heat to a singular state, whether it is solid, liquid or water, there will be a rise in temperature through application of heat. Whenever there is a single state present, whether it is only ice, only water vapor, or only solid, only liquid, only vapor, specific heat concept will be applicable. But whenever there is any two phases together, two states together, coexistence, solid liquid, liquid vapor, then there will be always be the application of latent heat at constant temperature, and that extra heat will be utilized to change the state entirely. Okay, so for different materials it will be different. I chose the simplest explanation through the simple experiment of ice, water and water vapor because it is easy to perform. Okay, so this is the concept of latent heat. Okay.